Following lecture will cover sections 2.4 to 2.9 in the text. Now that we know about calculating formal charges, we're going to focus specifically on carbon atoms with formal charges in section 2.4. The formal charge will affect the stability and reactivity of the molecules, which is one of the reasons why we need to be able to identify and calculate formal charges. Most carbon atoms will have 4 bonds and no lone pairs. However, we can have carbon atoms with a charge. The first carbon atom with a positive charge we're going to look at is called a carbocation. We're also going to look at a carbon with a negative charge, and that's called a carbanion. The carbocation has 3 patterns that we need to remember. So, a carbon atom with 3 bonds and no lone pairs and a positive charge is going to be a carbocation. In each of the cases in the example below, the carbon atom has 3 bonds, no lone pairs, and a positive charge. It may be helpful to draw in the hydrogen atoms if you're not seeing them. So, the first example, there are no hydrogen atoms. In the second example, there's a single hydrogen atom. And in the third example, there's 2. So in each case, each carbon has 3 bonds and no lone pairs, and that gives it the positive formal charge. The carbanion is just a carbon with a negative charge. Carbanions have 3 bonds and 1 lone pair. So, you should become familiar with these patterns. For example, we want to be able to use the patterns, draw in any lone pairs, and indicate the correct number of hydrogen atoms for each of the carbons. So if you'd like to pause the video and try the following examples, and come back and I'll show you how they're solved. Alright, hopefully you've had a chance to try the example. So we're going to draw in the lone pairs if necessary and provide the number of hydrogen atoms. For our first molecule, that's a carbanion. We have a negative charge, so we can draw the lone pair anywhere. You can draw it here, on the other side, it doesn't matter. Remember, the carbanion should always have 3 bonds and 1 lone pair. So we're seeing 2 bonds to hydrogen, 2 bonds to carbon, so there must be 1 bond to hydrogen. So there's a single hydrogen atom. The next one, we have a carbocation, positive charge. We see that our indicated carbon atom is bonded to 3 other carbons. Therefore, there are 0 hydrogen atoms here. The next example, we have a carbon atom with a negative charge, so that means it definitely has a lone pair. And remember, carbanions must have 3 bonds and a lone pair, so we're seeing 1 bond to carbon. So let's draw in the other 2 bonds, indicating there are 2 hydrogens here. The next example with the carbocation, there are no lone pairs. Carbon has 2 bonds to other carbons, so that means there's 1 hydrogen. The next example, our carbocation has a bond to another carbon, so that means there must be 2 other hydrogen atoms. And then the final molecule, we have a carbanion. We should draw in the lone pair. And carbon already has 3 bonds to 3 other carbons, so there are 0 hydrogen atoms. Carbon can have formal charges as well as other atoms such as oxygen and nitrogen. It's important that we understand the patterns for carbon, oxygen, and nitrogen. These are going to be the 3 most common that you encounter, and you need to know their patterns. Now, We can draw, you always have to draw a formal charge. However, drawing lone pairs is optional. All right, from here on out, you may not see them included. You're going to need to know where they are and how many lone pairs are present based on a given formal charge. For example, an oxygen atom that has a formal charge and one bond will have 3 lone pairs. Remember, we're trying to make sure that our atom has an octet here. So we have 8 total electrons around that oxygen atom. Oxygen has 3 possible bonding patterns in which the oxygen has 5, 6, or 7 valence electrons. So you're going to notice you're going to see 8 electrons around it, but remember, oxygen only has 6 when it's neutral, such as in the middle. So remember when we calculated formal charge, we gave 1 to oxygen and 1 to hydrogen, 1 to oxygen, 1 to the carbon. Okay, so oxygen here owns 2, 4, 6. That's how we get that, and it's neutral. Let's look at the other patterns. When an oxygen atom only owns 5 valence electrons, then it will have a formal charge of +1. When an oxygen, let's do that. So let's give 1 to hydrogen, 1 to oxygen, 1 to hydrogen, 1 to oxygen. We'll give 1 to oxygen and 1 to carbon. In this case, our oxygen atom owns 1, 2, 3, 4, 5, and it has a +1 charge. Here it had 6. And in our last example, let's look at our oxygen atom with a negative formal charge. We'll give 1 of those electrons to oxygen, 1 to carbon. And in this case, oxygen has 7. Make sure you know the bonding patterns. If you see an oxygen with a negative charge, it's going to have 3 lone pairs. If you see an oxygen with no charge, it's going to have 2 lone pairs. 3 negative, 2 neutral, and if your oxygen has a positive charge, it will have 1 lone pair. It would be helpful to memorize these patterns. Next, we're going to look at nitrogen. So nitrogen atoms can have formal charges calculated in the same way, but the bonding patterns are a little bit different. But you still want to remember these patterns. All right, if you see a nitrogen atom with a negative charge, it's going to have 2 lone pairs. If you see a nitrogen atom with no charge, if it's neutral, it's going to have 1 lone pair. And if you see a nitrogen atom that has a positive charge, it has no lone pairs every time. So I'd like you to pause the video, use the patterns from carbon, oxygen, and nitrogen that we just learned, and try to indicate the number of lone pairs that are on each of the oxygen or nitrogens. The oxygen atom, in our first example, if you recall, oxygens with a positive charge will have 1 lone pair. An oxygen with a negative charge will have 3 lone pairs. An oxygen atom that's neutral will have 2 lone pairs. And a nitrogen atom with a positive charge has no lone pairs. A neutral nitrogen atom has 1 lone pair. And anytime you see a nitrogen with a negative charge, it's going to have 2 lone pairs. Section 2.6 deals with 3D bond line structures. We've already gone over this, how to use the wedges and dashes to draw a 3D perspective. We covered this in section 110 when we discussed molecular geometry. However, just as a reminder, molecules exist in three-dimensional space, and we use dashes and wedges to show groups either pointing out of the plane of the paper or back behind the plane of the paper. Whenever you see a regular line, that's in the plane of the paper. In the following example, we have several molecules that have wedges and dashes to represent the 3D perspective of the groups that are attached. So I'm just going to draw in the hydrogen atoms on specific atoms so that you can see the attachment. So let's look at our first molecule. There's a carbon atom. You could draw a hydrogen with a dash there. We could have drawn a hydrogen here, right? There's one hydrogen because the carbon was bonded to three other things that are shown. What you don't want to do is draw a hydrogen here. That's not correctly representing the geometry of the molecule. For the next one, we have a carbon atom that has a bond to carbon, and it's got this dash to oxygen, which means there should be one other hydrogen. Now I could draw it above or below, it doesn't matter, it's still representing the same thing. There's a hydrogen there. And here we have an oxygen on this carbon with a solid wedge. So there must be a single hydrogen that would be represented with a dash. These hydrogens don't need to be drawn in, but it's often helpful to visualize where they're at. There's some other ways that we can represent molecules in 3D. The first is a Fischer projection. All right, Fischer projections are usually used for acyclic compounds or compounds that are not in a ring. Whenever you see that cross, think of it like this. As far as the 3D perspective is concerned, almost like that. And really, we could even go as far as doing that. Two wedges and two dashes. But we'll work on converting Fischer projections to bond line later. We're just introducing the fact that we have other representations for 3D structures when we're doing bond line. The next one is called a Haworth projection. That's for cyclic compounds. And the final one is just a regular bond line structure, but we want to take notice that molecules can be bicyclic, meaning we have two fused rings. So there are many bicyclic molecules. We'll cover that when we get to chapter 4. All right, the next section introduces resonance. So resonance occurs when more than one Lewis structure can be drawn for the same molecule. You may have seen some examples of this. Resonance is the movement of free electrons or pi electrons, meaning electrons that are in a pi bond. We're going to look at examples of both. And we can form other correct Lewis structures. So pi bonds, or the electrons in pi bonds, and the electrons that are responsible for formal charges are often spread out. And our bond line structures don't always show the true nature of where the electron density is. So an example is the allyl carbocation. There's your carbocation, and when you have an adjacent pi bond, that means it's allylic. So the allocarbocation has unhybridized p orbitals on each carbon atom. Our bond line structure is not representing that, but this is more, the second diagram more accurately depicts the orbitals and where the electron density is allowed. So what's really happening is that the overlapping p orbitals allow the electrons to move throughout the overlapping area. So we say the molecules has resonance and is delocalized. We're going to look at the application of resonance and drawing resonance structures in the following slides. So we said that resonance occurs when we can identify resonance occurring when you can draw more than one correct Lewis structure. So, for example, with our allyl carbocation, we could have put the double bond on the left, or we could have put our double bond on the right, and both are correct Lewis structures. Now, what's happening here is the electrons are moving between the different carbon atoms. Before we get into drawing resonance arrows and drawing resonance structures, there's a couple things about resonance structures that we need to know first. So the pi electrons here can exist on both sides of the molecule. These are your pi electrons. These are your pi electrons. When you see brackets, that indicates that resonance is occurring. So we use brackets for resonance structures. Resonance structures, like I said, don't truly represent the nature of where the electron density is. So they're kind of imaginary. We can use something called a resonance hybrid to more accurately represent the electron density. And when you see a double arrow, that's used for resonance. It's not equilibrium. Equilibrium double arrows look like this. The double-headed arrow, that's for resonance. So you saw the double arrow in Chem 1, and our double-headed arrow here is going to be for resonance. Now, when we draw a resonance hybrid, you'll notice that we have partial charges. Instead of having a formal charge on one of the atoms, here we have partial charges on both of the carbon atoms. That makes the molecule more stable when the charge is spread out and not localized on a particular carbon. When our charge is not localized, we say that it's delocalized, in which the charge is spread out over more than one atom. And this is what causes resonance stabilization. So when we can delocalize electrons, we stabilize the molecule. That's the reason that this happens. So the partial charges, again, are more stable than a full +1 formal charge. So the molecule undergoes resonance, or the electrons can move from different atoms into different bonds and vice versa due to resonance stabilization. Section 2.8 deals with drawing the curved arrows that you're seeing in resonance structures. We're going to learn the rules for drawing resonance structures, and then in our next lecture, we're going to learn several patterns so that you can begin to draw resonance structures on your own. But first, you need to master looking at the arrows and knowing what they mean. So, first, whenever you see a curved arrow, it represents the movement of a pair of electrons. So, an arrow like this represents 2 electrons. If you take Chem 3, you're going to see just sort of that half-headed arrow there. That represents 1 electron. All of our arrows are going to look like this, and it represents the movement of 2 electrons. Electrons always flow from areas of higher electron density to areas of lower electron density. So, one way to think about it is they flow from the source to the sink. The source is where we have negative density. The sink is where we have an empty p orbital, or a place of low electron density. The arrow always starts where the electrons are currently located, C in the pi bond, and the arrow is going to end, or points to, where the electrons end up after the movement. So if we were going to draw the resonance structure here, you can see how the electrons were currently located in this pi bond. We showed them moving to that carbon-carbon bond, all right, resulting in our positive formal charge moving. Now, if you're having a hard time seeing that, let me draw the hydrogens in. There's a hydrogen there, hydrogen there, hydrogen there. We have one hydrogen here. This one has 3 hydrogens. Carbon, carbon, carbon. All right, so when those electrons move, I want to represent this. We have a carbon that had 2 hydrogens. There's that carbon. Now the double bond is here. That carbon had 1 hydrogen. It was attached to another carbon that had 3 hydrogens. And this carbon had 1 hydrogen as well. Now, let's focus on this carbon. It has 3 bonds. I didn't break any sigma bonds. We just had the pi electrons move. So that gets the positive formal charge. So in chapter 3, we're going to talk more about using curved arrows for reaction mechanisms. All right, however, in chapter 2, we're learning curved arrows in resonance, in which we're never going to break a sigma bond. We can only move pi electrons in chapter 2. All right, there's 2 rules you got to know for resonance. 2 rules, really important. Never break a single bond or a sigma bond, okay? And don't exceed the octet rule for a second row element. If you break a sigma bond, you're going to end up with a fragmented molecule. And if you exceed the octet rule, okay, for any second row element, second row means that those elements have their valence electrons in the second shell, or second principal energy level. There's a 2s and a 2p in the second principal energy level. And in the S, you could put 2, in the P, you could put 6. That's a grand total of 8 electrons total in the second shell. You can't put any more electrons in there. So if you're representing a molecule that has more than 8 valence electrons, okay, that's an impossible structure. For example, let's look at the first one. If we move these electrons into the bond between the oxygen and the carbon, we'd end up with a double bond there. And that carbon would then have 1, 2, 3, 4, 5 bonds. That's a bad resonance arrow. In the next one, if we take the electrons and move them in between the oxygen and the nitrogen, that would put a double bond here. And we'd get rid of that pair of electrons. Right? Oxygen would have 2, 4, 6, 8, 10 electrons around it. You're violating the octet rule. You're exceeding the octet rule. And in the next case, when we have the electrons being moved between the oxygen atoms, you get a double bond. And we'd be exceeding the octet rule for the oxygen here. Now, you can have less than an octet, as in the case with the carbocation, but you can't exceed the octet rule. So one of the most important skills here in the beginning is being able to identify a valid resonance arrow using the 2 rules from the previous slide. Now, some things that might help you along in identifying valid resonance arrows are these 4 points. Sometimes it's helpful to draw the hydrogens in if you're having trouble seeing them. Make sure the tail of the arrow isn't ever located on a single bond, because that's going to mean we're violating the first rule, breaking a single bond. So tail of the arrow should never be on a single bond. Make sure the head of the arrow isn't putting the electrons on an atom that would exceed the octet rule. And if you're still not seeing it, try to draw the resonance structure that results from the movement represented by the arrows. So, for example, we want to inspect the arrow drawn on the following structure and determine whether it violates either of the 2 rules. So, here's our arrow. Here's the molecule, and there's the arrow of interest. When we move these electrons, the tail of the arrow is starting on a pi bond or a double bond. That's okay. So we haven't violated the first rule. And now let's take a look. I'm going to draw out, I have the Lewis structure drawn with all the carbons and hydrogens so you can see what's going on. We're going to check to make sure our second rule isn't violated. So when these electrons move as indicated by the arrow, that means the electrons from our pi bond are going to be moved in between each of these carbon atoms to form a new carbon-carbon bond. So the movement results in a double bond here. Now let's check. This carbon has 2, 4, 6, 8 electrons. That's all right. This carbon has 2, 4, 6, 8 electrons. That's all right. We haven't exceeded the octet rule. And now we can have less than an octet. This carbon has a positive charge, 3 bonds, and no lone pair, so it has a positive charge. This carbon here is an empty p orbital. Or an unhybridized p orbital. So this arrow is good to go. In the next example, I'd like you to pause the video and then try determining if the arrow violates the curved arrow rules for resonance. Remember, there's 2 rules. Don't break a single bond and don't exceed the octet rule. So, pause the video. When you come back, I'll show you the answers. All right, hopefully you've had a chance to give this a try. We're going to identify if the arrows violate our rules for drawing resonance arrows. All right, in our first example, if we move these electrons in between the carbon and the oxygen, we're going to end up with a double bond right here. Now that carbon had a hydrogen, that carbon had a hydrogen. The carbon will be fine, but if we put a double bond here between the carbon and the oxygen, we'd end up with 1, 2, 3, 4 bonds and a lone pair. That's 10 electrons. So we're violating the octet rule. For the oxygen, so that we're violating rule number 2. For the next one, if we put the electrons from the pi bond on the oxygen, this arrow is showing the pi electrons ending up here. So what we'd get rid of that, and we'd end up with a positive charge here. All right, we're not violating any of the rules. So this is a no. We're not violating any of the rules. We're not breaking a single bond, and we're not exceeding the octet rule for any particular atom. For our next molecule, if you put these pi electrons, okay, the tail of the arrow is not starting on a single bond, so we're not breaking rule 1. However, if we put those pi electrons in between the nitrogen and the carbon, we get rid of that, we'd end up with 10 electrons on the nitrogen. So yes, we are violating one of the rules, and we're violating the octet rule. In our next example, let's take a look. If we move the electrons from this pi bond, the carbon-carbon pi bond, to the other carbon-carbon bond, it will be a violation. Now, it's often helpful, like I said, to draw the hydrogens in. So you see carbon, carbon, there's one hydrogen here, there's that carbon. If you get rid of this double bond and put it right here, now look, we've got 1, 2, 3, 4, 5 bonds to carbon. So yes, this is a violation. We're exceeding the octet rule. In our next example, I hope you saw this immediately. When the tail of the arrow starts on a single bond, you know right away that this is going to violate one of the rules. So yes, this is a violation, and we're breaking the single bond. Violates the rules for resonance arrows. In our next example, we have a carbon atom that has a triple bond to a nitrogen atom. And we're going to take a pair of these electrons from that pi bond and dump them onto the nitrogen. So in essence, we'd be getting rid of a pi bond, we'd be putting that pair of electrons on the nitrogen. The carbon would impart a positive charge, and the nitrogen would impart a negative charge. So we're not breaking any of the resonance rules here. In the next example, we're taking the pair of electrons located on the nitrogen atom, and we're going to put it in between the carbon and nitrogen. So in essence, that pair of electrons is going to form a pi bond in between the carbon and nitrogen. And then that positive charge goes away there. We'd end up with a positive charge on the nitrogen. So, and that carbon had one hydrogen. So we're not breaking any of the rules. So this is a no, it does not violate any of our resonance rules. And in the last example, we have the tail of the arrow is starting on a single bond. So right away, we know that's a violation because that arrow is representing the breaking of a single bond. In section 2.9, we're going to look at formal charges and resonance. So it's important to always draw your formal charges for all resonance structures. Let's look at an example. If we're given the following structures, and curved arrows, we want to draw the resulting resonance structures and assign the formal charge. So let's pretend like you're not seeing this. Okay. Let's say you're just given the original resonance structure and the arrow here. And let's think about what's happening. I have a carbon atom that's sharing two pairs of electrons, has a pi bond there and a sigma bond, with an oxygen that has a positive charge and a lone pair. The tail of the arrow shows us that the electrons are moving from the pi bond to the oxygen atom. So right away, we can draw our oxygen atom, which had a lone pair. We're going to add that other lone pair. All right, now an oxygen atom that has two bonds and two lone pairs is neutral. That carbon atom, this carbon atom here, had no hydrogens. So we've got a carbon atom with no hydrogens and 3 bonds. Our carbon should have a positive charge. In the next example, let's pretend like that's not there. We're showing that the lone pair of electrons is being moved from the carbon atom to form a bond in between the carbon and the oxygen atom. So let's draw what that first arrow is representing. Okay. And now the second arrow is showing that the electrons from this pi bond are going to be moved onto this carbon atom. So now let's put that pair of electrons on the carbon atom, which already had a hydrogen. So now we've got a new pi bond that was formed, and you have a lone pair of electrons on the carbon atom. Notice the difference of an arrow that's representing electrons being moved to form a bond, and when electrons are being moved to form a lone pair. See, the first arrow is pointing towards the bond. That gives us a clue that a bond is going to be formed. And when you have an arrow that points towards the atom, that's typically a clue that a lone pair will be formed. And because we have a lone pair of electrons on a carbon atom that has 3 bonds, it should get a negative formal charge. The next important skill is, given a structure with curved arrows, draw the resulting resonance structures with the formal charges. It's often helpful to recall the bonding patterns for carbon, nitrogen, and oxygen with formal charges. So if you forget those, go back to your notes and review those patterns, because that's going to make your life a lot easier. Also, being able to see and know where the hydrogens are on a particular atom is also helpful. So what I'd like you to do is to pause the video and try to draw the resulting resonance structures for each example. Make sure to include formal charges. And when you're done, come back to the video and I'll show you the answers. All right, hopefully you've had a chance to try the following examples. So our first arrow on our first molecule is showing the electrons going from the oxygen atom to the bond. So we're getting a pi bond between the carbon and the oxygen. And then we have the other arrow showing the electrons moving from the pi bond to the carbon atom. And that gives us a negative charge. Why? Because that carbon had a hydrogen, still has a hydrogen. So carbon with 3 bonds and a lone pair has a negative formal charge. The next one, the arrow is showing pi electrons moving from one bond to another. We're just moving the position of the double bond. We're moving the position of the positive charge. In the next example, we have a lone pair of electrons that are going to be used to form a bond. And then the pi electrons are going from the bond onto the atom. The oxygen atom now is a negative charge. We're forming that new pi bond. And an oxygen atom that has 3 bonds and a lone pair gets a positive charge. In the next example, we have our lone pair of electrons that are going to be used to form a bond between the carbon and the other carbon. And then the pi electrons are going to be deposited onto the nitrogen atom. And a nitrogen that has 2 lone pairs gets a negative charge. There's several more examples of this in the homework, so make sure you give those a try. And finally, the next skill is you're going to need to be able to draw the curved arrows if I give you the resonance structure and all the formal charges. So in the last example, you were given the arrows and you had to draw the product. The next skill is, given both structures, can you draw the arrows in based on where you see the electrons ending up and how they're moving. So pause the video, give this a try, and when you're done, come back and I'll show you the answers. All right, hopefully you were able to give this a shot. Let's look at the first set of resonance structures. I see that my oxygen atom has a negative charge. Now, you'll notice that there are no lone pairs drawn. It's implied if that oxygen is neutral, it has two lone pairs. See, we don't have to draw the lone pairs in all the time. And an oxygen has a negative charge, and one bond has three lone pairs. So it looks like we have to show electrons moving onto that oxygen. Well, where did they come from? They came from this pi bond. So we're going to show that first pair of electrons moving there. And that pair of electrons left a carbon atom that had typically that had four bonds, and now that carbon atom has three bonds with no lone pairs, so it gets a positive charge. In the next example, we have to show an oxygen atom that's neutral becoming negative, so it looks like a pair of electrons from this pi bond have to end up on that oxygen. So we can show that with the first arrow. And then, oh, this is a typo. There should have been a double bond there, so that's my fault. The second arrow would be going from bond to bond. And this carbon had a hydrogen. When it moves, it will still have that hydrogen. So we have a carbon atom that has three bonds, no lone pair, it gets a positive charge. So make sure you fix that. That double bond should be there. All right, in our last example, we show the pi bond moving. So the electrons from that pi bond are going to move into that carbon-carbon system, and it's going to leave a positive charge behind. And that's the only arrow you need.